All right, so I need to first recap some of what we talked about last time because of the technical difficulty. Just remember what we were discussing were Yule processes, and what we have in a Yule process is an initial particle which lives for some random exponential amount of time with unit rate. Of course, this rate can be treated as a general parameter, but it doesn't change anything substantive. After that exponential amount of time, it splits into exactly two particles that are independent and identical to the first. And so the process evolves in such a way. Okay? And the process that we're interested in is the one that counts the value zt at each time t, where zt is the number of particles alive at time t. Okay. And so that's the process that we're interested in. And so the question that we are first going to ask, and that we actually proved last time, was a theorem, or we started to prove last time, the theorem which I'm writing as theorem 10.10, which is that for the Yule process, for a Yule process with a single initial particle, that e to the minus t, scaling the number of individuals alive at time t by e to the minus t. So the growth of this process is exponential in time. The growth of the number of particles is exponential in time. This converges almost surely to a random variable w. This is almost surely as t goes to infinity, where w is exponential with unit rate. Okay, so the number of particles alive at time t is scaling like an exponential random variable but it's growing exponentially fast. So that's the rate of its explosion, if you will. So this is a particle this is a pure birth process, in that it's purely fissioning into more particles as time goes on. Okay, so the first thing that we showed was the existence of this random variable. So the proof of this, we showed the existence of W using the L2 maximal inequality. And remember what that was, or how that came into play, was that we had that the probability of a soup of the absolute value of Sn, which is the absolute value of the deviations of S from its mean, bigger than alpha, is bounded by sigma squared over alpha squared, where Sn are the partial sums, the nth partial sums for independent random variables, independent mean zero random variables. Mean zero such that the sum of their individual variances adds up to a finite constant sigma squared. So we use this to show that the sequence of partial sums, this is the maximum deviation from the mean is zero, this is a Cauchy sequence, and Cauchy sequences converge and they have a finite limit. Okay, in this case. So we have the existence of a finite limit, and then we wanted to show that the limit is actually exponential. Okay? And the proof of this is a bit more interesting, it's interesting in that it allows us to exploit the recursive structure of the process, because by construction, so the proof, so we want to prove that W is unit exponential. Okay, and to prove this, think about how on the one hand we have a single process that we're interested in, which is ZT. So this is ZT. On the other hand, after an exponential amount of time t, we actually have two processes that we're dealing with, and they're independent copies. Okay, so we can actually look at the ZT process at a given time t. We have ZT here, but actually what ZT is if after this exponential amount of time t, we start over with two independent copies, Z prime and Z double prime. And what this is then, the number of particles in these two processes is Z prime at time t minus capital T. So this is the number at Z prime at t minus capital T plus Z prime at Z double prime at t minus capital T. Okay. So what we actually have is we have a distributional equality at time t, that ZT is equal in distribution to, leave myself some space, we have ZT equal in distribution to Z prime t minus capital T plus Z double prime t minus capital T. I really want to get this on one line, so let me Z prime t minus capital T plus Z double prime t minus capital T. Okay. And what we already showed is that we can scale this by e to the minus t, and what I'm actually going to do is I'm going to scale this by, I'm going to just write this differently so that the capital T's cancel, and that the index, the amount that we're scaling by, is exactly e to the minus time index. So by the theorem up here, we already know that this converges almost surely to W, some random variable. This converges, therefore, to an identical random variable, an independent and identical random variable W prime. Similarly, W2 prime. And e to the minus capital T, that's just a fixed random variable. It doesn't depend on time, the time index little t. This is actually a uniform random variable, because remember that an exponential random variable t is log or minus log of a uniform, and so e to the minus t is a uniform random variable. So we have this distributional relationship of the limiting variables W, and what we can show is that this distributional relationship means that W has to be a standard exponential random variable. And what I want to do is I want to first motivate why an exponential random variable would satisfy this property without actually proving it, and then we can go through the derivation, which is actually just a calculation, but it's actually interesting to see where you might get some insight into why this implies a exponential random variable. So think about, remember that the W's, so where, let's see, so the W's, where W prime, where did I put this? Where W prime, W2 prime are IID copies of each other, and U is a uniform, 0, 1. So remember the Poisson point process construction of the Yule process, but just in general, go back to what we know about Poisson processes, that if we look at a Poisson process, basic theory of Poisson processes, that the inner arrival times, we know that the inner arrival times are exponential. And so what we have here is the sum of two independent unit rate exponentials. So this is like waiting until the second time of occurrence in a Poisson process, right? So this is W prime, assuming these are exponentials, of course, W prime, W2 prime, okay? But this exact time here, okay, this is the sum. We can think about waiting some amount of time or picking, so if we condition on the value of this time, that's the time at which exactly the second occurrence happens. And so then the question is, conditional on the time of this occurrence happening here, at what point in this interval did the first occurrence happen? Well, the first occurrence is actually going to be distributed as W, okay? But how would we define the conditional distribution of where the first occurrence happened given the time of the second? Well, we already know that this is conditioning on, in a Poisson process, if we condition on the number of occurrences in a given interval, that the occurrences are uniformly distributed in that interval. So this value here, if we write this as U, if we take a uniform random variable on the length of time, right? The length of time is W prime plus W2 prime. And if we want to uniformly distribute something in that interval, we can just generate a uniform random variable and scale it by the length of the interval, right? But the time of the first occurrence is actually the same, has the same distribution as W, but this can also be obtained by taking a uniformly distributed variable, let's say W uniform on 0 to W prime plus W2 prime, which is equal in distribution to U times W prime, W2 prime. Okay, so that's some intuition for why this relationship holds for the exponential random variable, just in terms of the inner arrival times of a Poisson process and what we know about conditioning on the number of occurrences and then distributing the number of occurrences in an interval uniformly conditional on how many occurred. To actually calculate, what I'll do next is I'll actually calculate or show the calculation where it actually implies this relationship. So not just the fact that exponential satisfies this, but in fact this implies that it's an exponential random variable. Okay. So what we have and what's in the notes to prove that this implies that this distributional relationship that we showed, which we showed for the Yule process, remember we have a random time t, which opens up two independent Yule processes here, okay? And what we ended up with is showing that we have zt is equal in distribution to z prime t minus t plus z double prime t minus t. And what we already know is that this, if we scale this by e to the minus t, it has a limit. If we scale, we scaled this, so we have to scale both sides by e to the minus t. But we wrote this in a particular way to make it work out so that we could apply what we've already shown to get this relationship here. And we already know that e to the minus of a standard exponential is just a uniform random variable. So what we're trying to show is that the random variable, this distributional relationship implies that W must be an exponential. And we argued that exponentials satisfy this by what we already know of Poisson processes and their interarrival times to formally show the other direction that this implies exponential. One argument that's given in the notes is to derive what its moment generating function has to satisfy. That's a little bit more of a technical argument, and I'll leave that to the notes. The next thing that I actually want to do is to show an application of Yule processes to something called the Polya Urn. Okay, so the Polya Urn is so a Polya urn is, you imagine having an urn. It starts with, so you have an urn with little r red balls and little b black balls. So we start at time. So what we're going to do is we're going to start at time 0, where f of 0, we're going to define f of t, I should say. Define f of t to be the fraction of, let's say, red balls at time t. Okay, so what we do is, which is equal to the number of red balls at time t divided by the total number of balls in the urn at that time. Now, the way that the process evolves is that there's two ways to think about this, but we can think about it is we're going to draw a ball out of the urn at discrete time points, and we're going to draw a random ball from the urn, and whatever color that ball is, we're going to put the ball back, and we're going to replace it with an extra ball of the same color. Okay, so if we started with one red and one black ball, the first ball I pick, so we start with f0 equals to a half. The first ball I pick is red, say. Then I'm going to put that ball back, and I'm going to add an additional red ball in. So now I'll have two red balls and one black ball, and then at the next time I'm going to pick uniformly at random, again from the same urn, but this time I'll have a higher chance of picking a red ball, and so on and so forth. Okay, and so one question that you would ask, so here I've written it as if t can be either continuous or discrete. Let's leave it this way, but the way that I just described it was in a discrete time setting where, of course, we're going to just draw a ball randomly, at discrete time points. Okay. So now the question that we're interested in is, what's the limiting behavior of this fraction? So this fraction here is bounded between 0 and 1. And so it makes sense to ask, well, does this urn eventually settle down to an equilibrium? You might expect that it should, because as the urn gets bigger and bigger and bigger, more balls are in the urn. Then adding that single extra ball into the urn in that next draw is going to have a negligible effect on the contents of the urn. And so eventually, as we run this process farther and farther into the future, it's like we're sampling. It's like we're just doing regular sampling with replacement. Okay, because that extra replacement that we make in the urn doesn't really impact the probability of drawing certain balls in the future. Okay, but the question is, what is that limit? Okay, and it turns out that we can compute this limit, and actually the limit itself is a random limit. Which we can say, let f(n) N be a Polya Urn process with initially R red balls and B black balls, then the random variable Fn converges almost surely as n goes to infinity. I don't like this. So in a Polya Urn with R red balls and little b black balls to start. Okay. What we have is that the number of particles, or the fraction of red particles in the urn at time n converges almost surely to a random variable, which I'm going to write as y. Well, let's say g. A random variable g, almost surely as n goes to infinity, where g is a beta random variable with parameters r and b. So the parameters are r and b being the initial condition of the urn. Okay, so the limiting behavior of this process is heavily determined by a lot of what starts, a lot of where the process begins. So in the first draw of the urn, if it's one red ball, one black ball, and the first draw is a red ball, then that's going to have a lot of influence on where this limiting random variable ends up, as opposed to if the millionth draw is a red ball, that has very little impact on what the limit might be, because the outcome of the millionth draw actually depends on the million that came before it, and so it is actually being impacted by what happened early in the process. Okay. And now there's a number of ways to prove this, and we will possibly see a way to prove this in future lectures using martingales. But what we can actually do here is we can actually prove this using what we've already shown from the Yule process, and that's what I hope to do here. So even though this is described as a process in discrete time, what we can do is we can Poissonize. So this is a technique, Poissonization, where we take a discrete time process and we actually put it in continuous time by attaching exponential waiting times. And the reason we can, what allows us to do that, a lot of what allows us to do that is the memoryless property of the Poisson process. So in particular, let's assume, suppose we started with one particle of each color, okay? And I have a process where I'm going to run so what I'm going to do is I'm going to associate to each of these processes its own Yule process, each of these balls its own Yule process. And what does a Yule process do is it just waits an exponential amount of time and it creates a new copy of itself, right? So that's this doubling feature. So at exponential waiting times, we're going to pick that particular ball from the urn and we put it back along with a copy of itself. That's what the Yule process does. It's this binary fission, and in the Polya Urn process, it's doing something very similar. Okay, but since these are independent processes, and since the waiting times of a Yule process are exponential, the memoryless property of the exponential allows us to then discretize the hit times or the occurrence times of that Yule process so that it doesn't impact the limiting behavior. Okay, so what we have here is we have a process R, which is evolving in such a way, and R of t is just counting the number of red balls, right? And B of t is counting the number of black balls. Okay. But if we look at any given time and we count the number of balls, so there's 3 red balls at this time and 3 black balls at this time, then we can ask, well, what's the probability that the next occurrence comes from this process or comes from this process? Well, these are all IID exponential waiting times with rate 1, and so they each have the same probability of being the minimum of, so we're asking for the probability that the minimum of these 6 IID exponentials comes from this process versus that one. Well, they all have the same rate, so it's actually the sum of the rates of the good processes, the ones we want, over the total sum of the intensities, which is 3 over 6, which is 1/2, but that's exactly what it would be if we were drawing from the Polya urn with this composition at that time. Okay, so from this construction, what we can do is we associate to each ball. So we let RT be a Yule process with R initial particles, meaning that we have R independent Yule processes evolving, and we let BT be a Yule process with B initial particles. Okay. And we define the process that we're interested in, FT, to be RT over the sum of the number of particles at time t. Okay. And so what we want to do is we want to study the limiting behavior of this fraction by using what we already know about the limiting behavior of the Yule process. Now, what we know about the Yule process, so what we can do is, we're only a few steps away now, is that the R process has R initial particles. Okay. So there's R initial particles at time 0. And so it evolves. These evolve independently as before. And so what we know then from the previous theorem is that if we look at the limiting behavior of any one of these branches, e to the minus t times, say, r1t, this is r1, all the way out to rr. So we have r independent lines in the Yule process. Each one converges to an exponential, a unit rate exponential, and the sum, the process that we're actually interested in, is the sum of these independent processes. So they're going to converge to the sum of those limits, which is the sum of R IID exponential, unit rate exponential. So that's a gamma random variable. So this is going to be, so what we know is that e to the minus t RT converges almost surely to a gamma random variable with parameter R, okay, with rate R, shape 1. And by the same argument, the black ball process converges uniformly to a gamma with rate B, or with rate parameter B. And so now we're in a position to just, by this expression here, f of t, we multiply top and bottom by e to the minus t, And what we have is we have the top going to a gamma random variable, which let me write this as R infinity. Let me write this as B infinity, which is R infinity over R infinity plus B infinity, which we already know by basic properties of the gamma distribution that this is a beta random variable with rate with parameter RB. Okay. Okay. So this is one particular. So an additional argument that would have to be made now is that we've defined a process in continuous time. But what we want to do is we want to extract out the discrete time version, the one where we only look at the jumps in this process. So we look at the pure jump chain. But it's easy now, it should be easy to see that the pure jump chain in this process is actually just is going to be the Polya Urn process. And since the time index in both cases, the number of jumps in the discrete time case, which happen at discrete time points, and the number of jumps in the continuous time case are going to infinity, their limits will go to the same place, and that's going to be a beta random variable. So this is one particular application of a Yule process. It's an interesting application because what it actually allows us to do is use one process to study another, and use what we show about the limiting behavior of one process to generate the limiting, to say something about the limiting behavior of another. And the Polya Urn process is another is a classical example of what will be called a reinforcing process, or a process with reinforcement. And this is something that happens often in nature and in a lot of complex processes, particularly in networks, for example, which is an area that I've studied, where there's a tendency for individuals so if you look at a social network, there's a tendency for people who have a lot of friends to continue to accumulate more friends. There's a tendency for people who know a lot of people to meet more people, whereas people who have very few friends or don't have much of a social circle have very little outlet to meet people. So this is something called a rich get richer effect. This is a tendency for preferential attachment, or rich get richer in nature, in the sense that if you already have a lot of connectivity, or a lot of, in this case, if there's already a lot of red balls in the urn, that makes it more likely that the number of red balls is going to continue to accumulate because of this reinforcing structure. So this is something that I've personally studied quite a bit in the area of exchangeable random partitions and exchangeable random graphs and things like that. And it's just worth noting that the process that we described here is a realization, or is a statistic that comes out of an exchangeable process. So in the Polya Urn process, what we do is, one way to describe the Polya Urn is to an alternative description Polya Urn, is to define a sequence. So define a sequence of x's, x1, x2, and so on, by saying that xj is equal to 1 or 0 if the jth ball is a red ball, and 0 otherwise. So in this case, the number of red balls after n have been drawn is just the sum, the partial sum up to time n of how many red balls have been drawn so far, plus the initial number of balls, which is r. And the number of black balls is, well, it's n minus this, so it's n minus Rn. Well, let me not do that. It's n minus this sum. Okay. Plus the number of black balls that we started with. Okay. So this is another way of defining this process, but if we just look at the sequence of x's, the sequence of x's is not independent because we're drawing with this reinforcement. Right? When I draw a red ball to start, it's more likely that I draw a red ball on the second draw, and so on and so forth. But the sequence, so note, is that x1, x2 are not independent. Okay. But the sequence of these indicators is what's called exchangeable. So this is an exchangeable sequence of random variables. And it's actually an infinitely exchangeable sequence of random variables, meaning that it's an infinite sequence. So it's a sequence which is infinite. It has a property of exchangeability, meaning that for all finite n, the first k, the first n entries of this sequence are invariant to permutation. For all permutations sigma of the index set n. Okay, and that this is true for all n is that this is what's called infinitely exchangeable. So first exercise would be to prove this. So why is that? How is this true? Meaning that if I'm talking about 100, if I start with one red ball, one black ball, and I draw 100 times, that the probability that the first 50 are exactly equal, are all red balls, and then the next 50 are all black balls, is the same as the chance that I pick red ball, black ball, red ball, black ball, red ball, black ball. So that's a consequence of exchangeability, because if I have 50 red balls and 50 black balls and I permute them arbitrarily, that outcome, each of those outcomes has to have the same probability under an exchangeable distribution, and that's something that's satisfied for this binary sequence, this indicator sequence for the Polya Urn process. Okay, so that's an interesting and maybe not such an obvious consequence of this. But what's important to know about exchangeable sequences is that there's a strong connection between this limit, okay, and this sequence here. Okay. So this limit is a limit, so you can think about it as actually observing it in the infinite time limit of running this Polya Urn for an infinite amount of time, and it's a random variable. So in some sense, it actually is it's only observable after the fact. Okay? But this actually has a close connection in Bayesian statistics to what's called the prior distribution. So this is the prior. This actually is the prior distribution in a very precise sense of for this sequence, this sequence of exchangeable indicator random variables. Okay. So claim. Claim is to let y1, y2, etc. be constructed as follows. So what we do is we first take a random variable theta from the beta distribution with parameter RB, and conditional on theta, we let the yi's be conditionally iid. So now once we condition on theta, so what we're doing is we are generating a theta which is a random variable between 0 and 1. So that's like picking a random probability of heads and tails in a coin toss. And once we have this theta, what we're going to do is we're going to toss that coin independently to generate the values of y of this y sequence. So these are going to be conditionally independently Bernoulli random variables with parameter theta. So this is like doing independent coin tossing, but they're not independent. They're conditionally independent because what I first do is I pick a coin at random, and then once I have the coin, I toss it for all values. So it's important first to think, why is that different than independence? Okay. So after you know it, it's actually pretty obvious why that's different from independence, but it's important to actually think about why this setup actually produces something that's different from a purely IID sequence of coin tosses. And the next thing to show or to think about is that, well, first observation, then the resulting sequence of y's is exchangeable. Okay. So it's exchangeable. It has this property. And secondly, if we take the empirical the empirical mean, so if we take the partial sums, the sample mean of the first n of these, we take the nth partial sums, then this is going to converge to a random variable. Almost surely this is going to converge to a random variable y infinity, which is going to be equal in distribution to theta. It's actually going to converge to what theta is. So it's actually converging almost surely to theta. Okay. Now why is that? Well, if theta was just a fixed random variable, so if theta was just fixed, it's not random. So if we have a p coin and we toss a p coin independently for a large number of times, and the strong law of large numbers tells us that this empirical mean will converge almost surely to p, the proportion. The sample proportion converges to the parameter, the mean of the distribution. Well, in this case, the mean is actually random. It's a random variable drawn according to this prior distribution, beta distribution. But once we have it, we are just running an IID sequence according to Bernoulli theta. So just like in the usual strong law of large numbers case, we get convergence almost surely to whatever it was we were conditioning on. And we get this for every value of theta. Okay. So this is a consequence of something called Di Finetti's theorem. And let's see. I want to, maybe I'll leave this up for now. Okay. So here we have a claim, and this is actually a special case of a more general result called Finetti's theorem. So what Finetti's theorem says is this is actually a generic way of generating an exchangeable sequence is to first generate some random probability distribution and then sample conditionally IID from that distribution. So Finetti's theorem, and I'm just going to state it in the case where actually the setting in which Finetti himself stated it, which was assuming we have random variables on 0, 1 on the on just a binary set, just like we have here, coin tosses. But this extends more generally to any exchangeable sequence of random variables on a suitably nice space. But if we let x1, x2 be an exchangeable sequence with values in the set 0, 1, then there exists a unique probability distribution, a unique distribution pi, we'll call it pi, on the unit interval such that the x sequence, so the x sequence, so I'm writing bold x to be the whole sequence of x's. So the x sequence is equal in distribution to a sequence I'll call x star, where the way that we construct x star is first by drawing theta according to pi, and then by generating x star 1, x star 2, conditionally IID Bernoulli with parameter theta. So what this is saying is that every exchangeable sequence of random variables, infinitely exchangeable sequence of 0, 1 valued random variables, is a mixture of coin tosses where we first draw a random coin and then we use that coin to generate an IID sequence of coin tosses conditionally on the value of on what the coin is. Okay. And this relates to relate this back to the Polya Urn and to get back to what this claim here said. So what did this claim? This claim, first of all, just says if y is a sequence generated by the if y is a sequence that's generated from this process where we first generate theta randomly and then conditionally IID Bernoulli, that one, it's an exchangeable sequence and that its sample means converge almost surely to theta. Finetti's theorem kind of says the converse, which is that if we have an exchangeable sequence, then there actually is a unique distribution. It's unique, such that we can generate it in this way. Okay. Now, what we've shown in this what we've argued here in this description of the Polya Urn is that this sequence of x's that we construct from the Polya Urn by just as an indicator of whether or not it's a red or a black ball, that's an exchangeable sequence. Okay. Since that's an exchangeable sequence by Finetti's theorem, there is a unique probability distribution on the unit interval such that we could have constructed it in this way. Okay. But what we can, as a further corollary to Finetti's theorem, which we've already kind of argued down here, as a further corollary to Finetti's theorem. So the corollary is, and furthermore, that the empirical the sample means of xj converge almost surely to the random variable theta. Okay, so what we have in the case of the Polya urn, so for the Polya urn, what we already know is that we know that the ratio of the number of red balls to the number of all balls converges to, so what we already know is that the number of red balls over the total number of balls we know that that converges to almost surely to a beta RB random variable. Okay. But we also know that we can express this as on the top, this is R plus the sum of the xj up to time n. Okay, so we have this expression for the ratio of the number of red balls to the proportion of red balls in the urn. It's the number of initial red balls plus the number of new red balls that we've added over the total number of balls. And we can now scale top and bottom by 1 over n. And when we do that, what are we left with? Well, R and B are fixed, so as n goes to infinity, this goes to 1, so n over n, and little r over n goes to 0. And so what this actually converges to is just the limit of the xj's, the sample mean. So this converges to the same limit as this. But by Finetti's theorem, this is the limit of whatever, this is a random variable distributed according to this prior distribution. But by what we show with the Yule process, we know that this is converging to a beta random variable with parameter RB. So what this tells us, so this is theta in the Finetti expression. So what this tells us then by Finetti's theorem is that this prior distribution, so in Bayesian statistics, everything is conditional on the prior. And so what it says is actually the prior is unique. It's uniquely determined for an exponential random variable. And this gives us another interpretation of the Polya urn. Instead of as sampling with this reinforcement process, what we could do is we could just first sample a random variable from the beta distribution and then do IID sampling. And the parameters of that IID, the initial conditions of that process, are determined by the initial conditions of the urn, which is that we have the parameters beta RB. Those are the initial conditions. That's the initial composition of the urn. Okay. So that's a bit of a fast, bit of a crash course on exchangeability. There's a lot more that can be said on exchangeability that I won't talk about in this course, so I think I'll leave it at there for exchangeability and move on to the next topic in the next video.